there, and welcome to this Integrated Math 1 video series. This is the last video in this unit on correlation coefficient. Before we get into that though, let's go ahead and do our warm-up for today. 4 problems here for you. Go ahead and try to do those. Okay, in number 1, describe the difference between a linear function with a positive slope and one with a negative slope. Positive slope is you're increasing as we go to the right, so as x increases, the y increases. Whereas a negative slope decreases as we go to the right. So as x increases, y decreases. And so that's the main difference there between a positive and a negative slope. Number 2, if 6 is the third term and 22 is the 7th term, what is the 5th term? So we have 1, 2, third term is 6. And then 4, 5, 6, 7 is 22. What is the 5th term? If you remember back from the time we did the calendar problem and we looked at that interesting property of arithmetic sequences, it's always balanced throughout. So this middle number is going to still be the average of those two. So not only is the middle number the average of these 5 here, but it's also the average of these 3 or any 2 that are equidistant away from that number. So we can just average 6 and 22. So we get 22 plus 6 is 28 divided by 2 is 14. So 14 is here. And then if we wanted to, we could average these two to get this one. So 14 and 6 is 20 divided by 2 is 10. So you can start to see what's happening here. It looks like we have an arithmetic sequence with a common difference of 4. So from there we can create our explicit formula. If you want, you can go back to the second term would be 2 and the first term would be negative 2. So if you remember, our explicit formula is a sub n equals a1, which in this case is negative 2, plus the common difference, which is 4, times n minus 1. Or you could write kind of the linear function version of it, which would be a sub n equals, let's see, the slope is the same thing as common difference, which would be 4. So 4n plus the y-intercept, the 0th term, right? Because it's the y value when x is 0. So the 0th term would be right here, which actually would be negative 6. So it would be 4n minus 6. Okay? And you could get that same thing if you were to distribute this out and kind of simplify. Number 3, how do you know if a graph is a linear function? I hope you said something about a constant rate or a constant slope or a steady increase or steady decrease. Something like that would work. Or something about a line, a straight line, something like that. Number 4, what is the area enclosed by the line 3x plus 12 and the y and x axes? We did a problem like this, maybe last video or the video before, where you kind of create a graph and kind of see what's happening here. So let's do that. So we have our y-axis and our x-axis. 3x plus 12 has a y-intercept of 12 and a slope of 3. So if we were to go to the right, so every increase of 1 in x, we're going to go up 3. Which means if we go a decrease in x of 1, we're going to go down 3. So we could go down 3 over 1. That would be at 9. Over 1 down 3 more, which would be at 6. Over 1 more time, it would be down to 3. And then the last one here would be at 0. So it's a y-intercept of negative 4. So if we were to plot this line here, it would look something like that. So this is the triangle that's created with the linear function, the x-axis and the y-axis. And so the area in here is what we're talking about here, so it's the triangle. And again, the triangle is always half the rectangle that would go around it, like we talked about last time. So the rectangle would look something like this. All right, so that triangle is always going to be half of that. So, which is where we get the area equals 1/2 base times height, the base and height, or the length and width of that rectangle. And so we get area equals 1/2, base would be 4, times the height would be 12. So we get, really it's 4 times, if we take half of 12 would be 6, it would be 4 times 6 would be the same thing, would be 24. So 24 would be the 24 units squared would be the area of that enclosed area. Okay, so let's go ahead and hop into our lesson for today, which is, we really have 3 goals. One is to calculate the correlation coefficient. Number 2 is to interpret that correlation coefficient. And then number 3 is understand the difference between what we call correlation and what we call causation. And it's a very important difference between those two, and we want to make sure and address that in this video today. So if we think about correlation, correlation is how tightly clustered points are around a certain line. Okay, so if things are really, really spread out, they're not very correlated. Okay, and then if they are kind of tightly clustered around the line, the points kind of form a line, then it's very high correlation. If it's an increase, so it's a positive slope, then it's going to be a positive correlation. If it's a negative slope, then it's going to be a negative correlation, because those are inversely varied. And so we can have positive, we can have negative, and we can have no correlation. We can also have strong and weak correlation. So if it's a strong correlation, like it pretty much follows a line. Like, it's not perfect, obviously, but you can very much see the line of best fit happening there. If you go back to our last video talking about line of best fit. If you can kind of see it, but it's not really a good fit at all, then we might call that a weak correlation. And then of course we have a strong negative, which is a very strong, but with a negative slope. So there are, there are certain values that we associate with this, and numerical ways that we can analyze this. If we go to our videos from last time, so this was the number of thousands of people in Iceland. We look at our population here. So I said we would come back to these values later. We're going to talk about that right now. So let me bring you up here so you can see this. Here's our line of best fit from last time. Right here we have 2 numbers here. We have r squared and we have r. R squared we won't worry about right now. Let's focus on r. R is 0.9969. Okay, the greatest correlation you can have is 1. Right, so this r represents the correlation. That's the purpose of our video this time, right? So 0.9969 is very, very strong. Okay, it's almost perfect, but it's very, very strong. And you can see that it's positive because it's got a positive slope. But you can see why it's very strong, right? Because the line is almost a perfect prediction or estimation of these points. And so that's what we mean by correlation in terms of a numerical value. They can go from -1, all the way to 1. This is where we have strong positive. Over here we have strong negative. And in the middle, around 0, we have no correlation. And there's not necessarily like a strict cutoff to where these are separated, but just kind of use your number sense and intuition through here. So strong positive, we might say, is in here all the way to 1, strong negative in here, and then no correlation, is around 0. So somewhere in there. In between those, you might have, a weak. In between here would be a weak negative, and then in here you would have a weak positive. So again, there's not necessarily strict cutoffs to these. I would say anything, less than 0.3 would be no correlation. Anything above 0.3 but less than like 0.7 could be a weak. Anything above 0.6, 0.7 might be a strong correlation, that kind of thing. But it ranges from -1 to 1. Again, negative doesn't necessarily mean anything bad. It just means the data is decreasing in a negative slope. It doesn't make it any less strong or whatever. In fact, -1 is stronger than like 0.9, for example. Okay, here's an example. We have U.S. TV viewers and estimated TV show downloads. And overall, I mean, if you were to try to, like, in your head picture the line of best fit, like, I don't know where I would draw it exactly. If you don't know where you would draw it, if you cannot picture the line of best fit, that's a great indication that it's no correlation. All right, let's look at another example. So this was the Iceland one. This is the millions of users for Amazon Prime that we looked at last time. The R here is 0.972, so not as good as the one we did last time with the Iceland population, but it's still pretty good. And so overall, these points kind of form a linear shape or whatever. So 0.97, pretty good. And then lastly, not really as good though. It's not as tightly clustered around that line. And as you can see, the correlation here is 0.52. 0.52, because the data is more spread out. It's not aligned with that line of best fit. So 0.52, I would still say it's weakly correlated, but not necessarily strong correlation there. All right, let's look at some other examples. And we're going to start talking about this too. And this is a very important conversation to have. Just because two things are correlated does not mean that one causes the other, unless that's the only factor in the whole situation. Okay, so if there's only one thing that can impact the outcome, and they're correlated, well then of course there's some causation there. But there are a lot of studies out there, a lot of reports that say that two things are correlated, and everybody hops to the conclusion that this one causes this other thing. For example, one that's common is diet drinks, Diet Coke. And there are studies out there that show that Diet Coke is correlated with heart disease and some other things, even death. But just because those are correlated does not mean that it's the Diet Cokes that are causing those things. There are other confounding variables involved there. It could be that more people that drink Diet Coke are more worried about their weight, and so that there's some other things going on there, other health issues. Maybe people that drink Diet Coke also maybe smoke or something. So there could be other lurking variables that we don't know about, that we're not factoring in. Now, if we can eliminate all of those and say that those are not causing this, then we might be able to say that Diet Coke is causing these things. But just a correlation is not enough to show the causation. And I hope I give you some examples of maybe why that might be. So let's look at some different examples, and let's talk about correlation versus causation, and see if we can hammer this out. All right, so we got here rushing yards per game, so the number of yards the team has rushed for, and then the points per game. You might think that the more rushing yards or the more points per game you have, the greater number of rushing yards you might be able to get in a game. And it shows that they are, at least pretty good correlation there. I don't know what the correlation coefficient there is, but it looks fairly strong and positive. Maybe not the strongest of correlations, but we cannot say that it's simply the points per game that's causing the rushing yards. Is that a variable? Yes. Okay. Does it have something to do with it? Yes, but is it the factor? Not necessarily, right? And so that just kind of gives you an example. We cannot jump to that conclusion without narrowing down all the other likely variables that are involved. Okay, here, exam score. This is an example of a negative correlation. So exam score and the number of missed classes. As the number of missed classes increases, overall it looks like the exam scores are going down. So that's a negative correlation. I would say that this is a moderately strong negative correlation. Maybe 0.7, 0.8, or sorry, negative 0.7 or negative 0.8 in that region there. All right, so you can see a negative correlation there. Does the number of missed classes cause the exam score to go down? You could probably argue one way or the other. Have we eliminated all other variables? We haven't, right? So there could be other things going on there. We can't say that missing classes causes the exam score to go down, but you might consider that and think about what are the other variables involved and see if we can eliminate those and narrow that down to just the missed classes that are causing those. Obviously, it has something to do with it, right? All right, how about ice cream sales and sunglasses sold? Looks like a positive correlation there, right? Does that mean that the number of sunglasses sold caused the number of ice cream sales to increase? I think this one's pretty clear here. There's a lurking variable involved, right? When does the number of sunglasses sold occur? In the summertime, right? When it's bright outside. When does the ice cream sales increase? More people can buy ice cream in the summertime, right? And so there's this lurking variable of time of year that's happening here, and so we cannot say that one is causing the other one. To bring home the point even more, we have along the x-axis here the number of pairs of blue socks owned and the baskets made in a game. Okay? Looks like the number of baskets made in a game increased as the number of pairs of blue socks owned increased. Does that mean the number of socks owned caused the number of baskets to increase? I think not, right? There are all kinds of things out there that show that two things are correlated, but it's obvious that they're not causing it. For example, shoe size and vocabulary. Your vocabulary, like the number of words you have in your vocabulary, especially early on in your life, increases dramatically, right? As you go from maybe zero to 12 years old. Also, your shoe size increases from 0 to 12. Does that mean that your shoe size increasing caused your vocabulary to increase? I don't think so, right? And so, again, a number of different reasons. We cannot jump to conclusions and assume that correlation means causation. Now, it might get you to question things. It might, change some habits of yours, because maybe the group of people are more likely to do certain things or have certain side effects or whatever. But overall, we cannot jump to conclusions and assume that correlation means causation. There's a big difference between those two. You really need a scientific, experimental design, with two groups to really discern, what's causing things. This is more of like an observational study where we're observing, collecting data, and then seeing if there's a correlation. That's really all we can do, though, is see if there's a correlation. We cannot determine causation. All right? So with that, let's do one more of these and see if you can calculate the correlation coefficient. Okay, so what I want you to do is take these points here and see if you can find the correlation coefficient between them. All right, so what I've done here is I've taken, I'm just going to show you my calculator as I did last time in our last video, and I have, let me start over here. If you go to stat, which is next to the arrows here, over and just hit enter on edit, and I've typed those numbers in there just like we did in our last video. So what I'm going to do now is I'm going to go to stat calc and go down to linear regression, and I'm going to go all the way down to calculate and hit enter. And I see my A value, which is the slope, my B value, which is the y-intercept. I see r squared and r. We're going to focus on r, which is the correlation coefficient. It is negative 0.96546 approximately. So it's a very strong negative correlation. If you don't see these last two rows here, go back as I showed you last video, hit mode, go up to stat diagnostics and turn that on, and then redo your linear regression, and it should pop up at that point. So that's how we calculate correlation in our calculator. Go to stat, edit, type in the numbers, and then quit out, go stat, calc, to linear regression, which is where we get our line of best fit. And in that same calculation, it will also give you the correlation coefficient. All right, so that's it for this video. I hope we were able to reach our goals for today, which were to calculate the correlation coefficient, interpret the correlation coefficient, understand the difference between correlation and causation. Again, that's it for this unit. I hope you'll join us in this next unit for Integrated Math 1 video series.